ArgoCD, the GitOps hero in your DevOps story. Imagine you're a DevOps engineer managing dozens of microservices deployed across Kubernetes clusters. You've automated builds, tests, and containerization, but deployments still feel like a fragile, manual, error-prone process. YAML files are scattered, environments drift out of sync, and sometimes a quick fix breaks production because someone edited a manifest directly in the cluster. This is where ArgoCD becomes your trusted companion in the DevOps journey. What is ArgoCD? ArgoCD, short for Argo Continuous Delivery, is a GitOps tool designed specifically for Kubernetes. Instead of deploying apps manually or through ad hoc C scripts, ArgoCD treats Git as the source of truth. It watches your Git repositories for changes in Kubernetes manifests, YAML files, Helm charts, or customized configurations, and applies those changes automatically and safely to your clusters. In short, Git becomes your deployment dashboard, and ArgoCD is the intelligent agent that makes sure your cluster stays in sync with it. How it works: spot on. You define your Kubernetes resources in Git, using raw YAML, Helm, or Customize. 2. You register the app in ArgoCD, pointing it to the Git repo in the target cluster. 3. ArgoCD continuously watches both Git and your cluster state. If someone commits a change, like updating an image tag, ArgoCD detects the difference and updates the cluster pod. 5. You get a clean visual interface that shows whether the live cluster is synced or out of sync with Git. 6. It supports autosync or manual approval workflows, depending on your compliance needs. A day in the life with ArgoCD. Let's say your team pushes a new feature to the main branch. That push triggers C, maybe GitHub Actions or Jenkins, to build a Docker image and push it to your registry. It then updates the image tag in a Kubernetes manifest inside your Git repo. At this point, ArgoCD kicks in. It sees the commit, notices that the live cluster still uses the old image tag, either prompts you via the UI or CLI, or, if autosync is on, updates the deployment in real time. No more kubectl apply commands. No more guesswork. And if someone tries to change a resource manually in the cluster, ArgoCD notices the drift and tells you, or even rolls it back to match Git. Why DevOps engineers love ArgoCD. On. Declarative plus version controlled. Everything is traceable in Git 2. Cluster drift detection. It catches config changes not made through Git 3. Multi-cluster support. Manage all your clusters from one dashboard. 4. Rayback plus SSO. Secure and compliant by design. 5. Health checks. Built-in logic to detect if apps are truly ready, not just deployed. How it fits in the DevOps toolchain. On. Combine C, Jenkins, GitHub Actions, GitLab C, with CD, ArgoCD. Use it alongside Helm, Customize, Vault, Terraform, or Flux. 3. Integrates well with tools like Prometheus, Grafana, and Slack for monitoring and alerting. Real impact. ArgoCD brings peace of mind to DevOps teams. It closes the loop between development and deployment. Instead of chasing down what's in production, you always know it's exactly what's in Git. Limitations. 1. Security and secrets management. No native secrets management. ArgoCD does not securely manage secrets on its own. It requires integration with tools like A. Sealed secrets. B. HashiCorp Vault. C. External secrets operator. Risk. If secrets are stored directly in Git, unencrypted, it's a big security hole. 2. Learning curve. ArgoCD introduces GitOps concepts that might be new to teams used to traditional C/CD. Requires good knowledge of Git workflows, Kubernetes, YAML structuring, especially with Customize or Helm. 3. C/CD separation. ArgoCD is CD only. It does not build, test, or push containers. You still need a separate C tool. For example, Jenkins, GitHub Actions, GitLab C. No native build pipelines like Tekton or Jenkins. 4. Performance with large repos. If your Git repository is very large or has many environments/apps, syncs can become slow. Memory/CPU usage on the ArgoCD controller increases. Solution. Split large monorepos into smaller ones, or use app-of-apps strategy carefully. 5. Autosync isn't always enough. Autosync only handles what's in Git. It doesn't automatically roll back or retry failed deployments unless you explicitly configure that. No intelligent canary or blue/green deployment strategy out of the box, though it integrates with Argo rollouts for this. 6. Helm chart complexity. Helm users can hit issues when ArgoCD doesn't render templates the same way your local Helm does. Values files get messy across environments. Helm secrets are especially tricky and require additional tools like Helm secrets. 7. Limited observability. While ArgoCD has a clean UI, it lacks built-in deep metrics/logging/alerting. You'll likely want to pair it with Prometheus plus Grafana, or forward logs to ELK/Loki. 8. Multi-tenancy is limited. ArgoCD supports airbag and projects to isolate users/apps. But true multi-tenancy, like complete isolation between teams or business units, needs careful design and often external enforcement via OPA/gatekeeper or namespace policies. GitOps. GitOps is a modern DevOps practice that treats Git as the single source of truth for infrastructure and application configurations. Instead of deploying code or changing environments manually using scripts or command line tools like kubectl, GitOps introduces a declarative and automated approach to managing systems, particularly those based on Kubernetes. In a GitOps workflow, everything begins with Git. The desired state of your system, whether it's a Kubernetes deployment, a service, or a configuration file, is defined in code and stored in a version-controlled Git repository. This definition might take the form of raw YAML files, Helm charts, or customized templates. Git is not just used for storage but becomes the canonical source that declares exactly how the system should behave. A GitOps operator, such as ArgoCD or Flux, continuously monitors the Git repository for changes. When a developer makes a change, for example, updating the image version of an application, and pushes it to Git, the operator detects this and automatically applies the update to the Kubernetes cluster. This means that deployments are triggered by Git commits, not by manual intervention. An essential part of GitOps is the reconciliation loop. The GitOps tool continuously compares the actual live state of the cluster to the desired state defined in Git. If it detects any drift, whether caused by human error, manual overrides, or failures, the tool can either alert the team or automatically bring the system back into alignment with what's defined in Git. This ensures a self-healing system where the infrastructure constantly converges toward the declared state. Another major advantage of GitOps is traceability. Since all changes pass through Git, there's a full audit trail showing who made what change and when. Rolling back to a previous configuration is as simple as reverting a Git commit. This gives DevOps teams confidence, control, and a clear history of system changes. While GitOps introduces many benefits, like speed, reliability, and repeatability, it also has its challenges. Managing secrets securely is critical, as Git is not a safe place for plain text credentials. Structuring large repositories, managing multiple environments, and handling deployment strategies like Canary or Blue/Green also require thoughtful planning. In essence, GitOps is a philosophy and set of practices that merge the best of Git workflows with infrastructure as code and automation. It empowers DevOps engineers to manage complex systems in a scalable, secure, and transparent way by simply working through Git. Handling secrets securely in GitOps. Handling secrets securely in GitOps is a critical topic because Git is inherently unsafe for storing sensitive information like passwords, API keys, and certificates. However, since GitOps relies on Git as the single source of truth, we need a strategy that allows us to represent secrets in Git without exposing them. The problem: in a standard Kubernetes setup, secrets are defined in YAML like this. API version, v1. Kind, secret. Metadata. Name, MySecret. Type, opaque. Data. Password, bzilts1izxr_kicksends29yeza ==. The data field is base64 encoded, but not encrypted. If you commit this file to Git, anyone with access to the repo can decode the secrets. That's not secure. GitOps compatible secrets handling approaches. Spot 1. Sealed secrets, Bitnami/Kubernetes. Sealed secrets is one of the most GitOps-friendly tools available. Here's how it works. You encrypt your secrets locally using a public key provided by the sealed secrets controller running in your cluster. The encrypted sealed secret is committed to Git. Only the controller, which has the private key, can decrypt the secret and convert it into a real Kubernetes secret during deployment. Because the sealed secret is encrypted, it's safe to store in Git. And since it's declarative, it's compatible with GitOps tools like ArgoCD or Flux.2. External Secrets Operator, ESO lets you reference secrets stored in external secret managers such as AWS Secrets Manager, HashiCorp Vault, Google Secret Manager, Azure Key Vault. With ESO, you don't store the actual secret in Git at all. Instead, you commit a Kubernetes external secret resource to Git, which just points to the actual secret in the external system. At runtime, ESO fetches the secret and creates a Kubernetes secret dynamically. This is a great option if you already use a cloud provider's secret manager or Vault 3. SOPs, Mozilla, plus Customize or Helm. SOPs, Secrets Operations, is a tool that encrypts specific fields in YAML files using KMS or PGP keys. You encrypt only the sensitive parts of the YAML, like passwords, and commit the encrypted file to Git. SOPs can be integrated with A. Customize using the Customize SOPs plugin. B. Helm using tools like Helm Secrets. This allows you to store encrypted secrets in Git and still use GitOps tools to deploy them. A typical GitOps workflow with sealed secrets. 1. Developer creates a Kubernetes secret manifest. 2. Uses kubectl CLI to encrypt the secret, producing a sealed secret. 3. Commits the sealed file to Git. 4. ArgoCD syncs the manifest pod. 5. The sealed secrets controller in the cluster decrypts it and creates the actual secret. The result, Git stays secure, your cluster gets the secret, and the process is declarative and auditable. What not to do? Never store unencrypted Kubernetes secrets in Git, even in private repos. Don't rely on base64 encoding. It's not encryption. Avoid custom in-house encryption scripts unless absolutely necessary. Stick to trusted tools. In summary, GitOps-friendly secret management means you encrypt secrets before storing them in Git, sealed secrets, SOPs, or store references to secrets in Git and pull the real values from a secure backend at runtime, external secrets operator. Both methods maintain the declarative, version-controlled nature of GitOps while keeping secrets secure and compliant.